In this video, we're going to do an introduction to polar coordinates and graphs. So polars are a completely different way at looking at equations and points, and we're going to talk about the differences. All the things we've done before have been in the Cartesian plane or the rectangular plane. And we've always used x and y coordinates when we have represented points and lines. Prior to learning about polars. This should say polar here. In the polar plane, we refer to everything in terms of r and theta. When we talk about the polar plane, we don't talk about the x and y axis, but rather we talk about the pole, and this is the polar axis. And when we refer to angles, we refer to the angle theta as the distance from the polar axis. So for example, this is what a polar graph would look like. It's circular in nature. You'll see that 0 over here is in the same spot as the positive side of the x-axis. And the center we don't refer to as the origin, but we refer to that as the pole. You'll also see these concentric circles, or these circles going out from the pole. Those have measures of 1. So these are units of 1. So this would be 1 unit away from the pole, 2 units away from the pole, 3, 4, 5, etc. So this distance here is what we call r, and that's how we can represent points in the polar plane. So here we have the point 2 comma pi over 3, and I want to represent it in 3 different ways. So let's start with plotting the point first. We're going to look for pi over 3, which is here, and then we're going to go 2 units away on that line from the pole. So if I go out 2 units, I end up right here, and that is the point 2 comma pi over 3. Now, the cool thing about polar coordinates is that you can represent points in different ways. In the Cartesian plane, you're limited to x and y, and there's really only one representation for every point. In the polar plane, because you can continue to go around in circles, you have an infinite number of representations for any point. So what I mean by that is this. This point 2 comma pi over 3 can be just this angle pi over 3 and then 2 units away from the pole. However, it could also be the angle where you go around 2 pi and then come back to here, right? So that angle would be 2 pi plus pi over 3, and it gets you back to the exact same spot. Okay, so as you can see, there could be an infinite number of representations for that same point because I can continue to rotate around the pole and just keep adding 2 pi to get different angle measures. We wouldn't normally write it like that. We would write it as 2 comma 2 pi would be the same as 6 pi over 3. So then we would write that as 7 pi over 3. Right, so that's one additional representation. Let's talk about a few others. Instead of rotating in the positive direction, I could rotate in the negative direction. Remember, we learned about this when we were doing trig. We said, well, if you rotate in the opposite direction, then your angle is just negative. And so I'm still 2 units away from the origin, but instead of rotating positive pi over 3, I'm rotating negative 5 pi over 3. And how do I know that's negative 5 pi over 3? Well, if I just do pi over 3 minus 2 pi, that'll get me that 5 pi over 3, right? Because I'm rotating around this way. So that's a second representation. A third representation allows us to flip over the pole. If you were to look at this point on this line, if you look at this line here, the line pi over, where it is on pi over 3, if you were to go across the pole, like literally just jump over the pole or go 180 degrees around or pi units around, you would be at 4 pi over 3. Okay? So I can actually write this point on this side of the pole and then just negate the r value, and that flips it back over the pole. So I can actually write this point as a negative 2 comma 4 pi over 3. And so what that says is, hey, let me go around a 4 pi over 3. I'd be here at 2, but that negative means I flip back over the pole, and that puts me back where I started. So those are 3 different representations. You can add 2 pi radians to the angle, you can rotate in the reverse direction, or you can jump over the pole or reflect over the pole by negating the r value. Now we also need a method for converting between rectangular coordinates and polar coordinates. These are the equations that we're going to use to do that. These first 2 equations, you'll notice we have x and y in terms of r and theta. So that's going to allow us to convert from polar coordinates into rectangular coordinates. I'll show that in problem number 1 here. So we've got x is equal to r cosine theta, and y is equal to r sine theta. If I go ahead and plug in my r and my theta, I would have 2 times the cosine of 3 pi over 2. And here I have y is equal to 2 times the sine of 3 pi over 2. Now, cosine of 3 pi over 2, if you don't remember, you could always just draw yourself a quick sketch of your cosine curve and your sine curve. Right, here's 1 and here's negative 1. Here's 1 and here's negative 1. I know at 3 pi over 2 I'm right here and I'm right here. So for the cosine graph, 3 pi over 2, the cosine of 3 pi over 2 is 0, so this would be 2 times 0 or 0. And for the y-coordinate, the sine of 3 pi over 2 is negative 1, so this would be y is equal to 2 times negative 1 or negative 2. So the rectangular version of this point would be 0, comma, negative 2, which hopefully makes sense, because if you were to plot 2 comma 3 pi over 2 on the polar graph, you'd go around to 3 pi over 2 and you'd go down 2 units. And if you think of that, if you were to kind of superimpose that on the rectangular coordinate system, right, this would be your y-axis, this would be your x-axis, and you're literally at the point 0, comma, negative 2. Okay, so that's how you would convert from polar to rectangular. If we're going the other way, we're going to use these other equations. Okay, so I have an x and a y value I need to convert into r and theta. So I'll start with my x squared plus y squared is equal to r squared. So I have negative 1 squared plus root 3 squared is equal to r squared. That would be 1 plus 3 is r squared. R squared would be 4, so r would be 2. And now I know that the tangent of theta is going to be root 3 over negative 1. Think about where that is. So negative 1 root 3 is up here in this quadrant. Okay, so I'm saying the inverse tangent. So theta is going to be inverse tangent of root 3 over negative 1. That I can do in my calculator. So if I go to my calculator, make sure you are in the proper mode. I'm going to change mine into, actually I could leave it in radians, but I'm going to do it in degrees just because I think it's a little bit easier to understand what's going on that way. And if I do second tan of root 3, close my parentheses, divided by -1, I'm going to get negative 60 degrees. So think about what's happening. Negative 60 degrees would put me down here in the 4th quadrant, right? But the problem is the original point was up here in the 2nd quadrant. So what I want to do is I want to add 180 degrees to that to get me where I need to be. Okay, so if I add 180 degrees to that, if I add 180, that would put me at 120. Right, that puts me at 120 degrees. In radians, 120 degrees is just going to be 2 pi over 3. Okay, so my point is 2 comma 2 pi over 3. We also have some other equations, or we have rather equations that we can also convert into polar form, and I'll do that in the next video.